We're still having a couple people roll in, but I appreciate you all being here. My name is Kyrie Baker. I am representing EPRI, the Electric Power Research Institute, as well as University of Colorado Boulder, where I'm a professor. I'm co-hosting this webinar with Priya Danti, who's at Climate Change AI and Carnegie Mellon. And this is a very exciting session where we're going to get to hear from grid operators all over the world about what they think about different applications and opportunities of artificial intelligence within power grids.
Yeah, so today we'll be diving into a couple of different questions in the GPST research agenda. So the GPST, Global Power System Transformation Consortium, is a consortium of some of the leading power system operators around the world, aiming to basically transition to low emissions, reliable power grids in a very rapid manner. About a year ago, they put out this research agenda, which basically represents the results of a multi-month process of really trying to identify what kinds of questions need to be answered on the research side in order to facilitate this transition. The research agenda itself is methods agnostic, which is to say it is focused on the problems that need to be solved rather than the specific methodologies that are needed to address those. That said, today's event focuses on AI and machine learning. So a number of these research questions may be facilitated by methods in AI and machine learning. And today we're going to focus in on 3 questions from the research agenda, which may be particularly suited. So one of those questions focuses on near real-time system monitoring and control with large quantities of inverter-based resources. So things like, rooftop solar power or solar power in general. And so this is a question of control, which might be amenable to reinforcement learning and control methods from AI and machine learning. Another question that we'll be addressing is regarding, dealing with uncertainties in weather conditions that impact power loads as well as renewable energy output, and how better forecasting techniques and probabilistic forecasting techniques potentially help with that, which is potentially amenable to time series forecasting techniques from AI and machine learning. And then the third question we'll focus on is around planning, using probabilistic planning methods and tools in order to plan power systems with large shares of, time-varying inverter-based resources. And these are potentially amenable to techniques that use AI and machine learning in the loop of optimization and planning, for example. So we will, for each of these questions, we'll have the system operators present for about 10 minutes and then open up a Q&A for each specific question for 10 minutes. And then we'll also have some open Q&A and discussion at the end. And the goal of this event really is to provide a starting point. We really want this to be a jumping off point for those who are coming from the power systems research communities and AI and machine learning research communities to work together on tackling some of these problems that the system operators have identified as being of real importance to addressing the transition of power grids. And doing so in a way that's cognizant of the actual challenges that are being faced on the ground, and maybe some of the assumptions that some of the ways in which maybe the assumptions that we often make in research may not translate to practice, being cognizant of that so that these methods can actually translate to practice. So this is meant to be a starting off point and a jumping off point for sort of further concerted work on this front. Kyrie, I don't know if there's anything you wanted to add.
Yeah, thanks, Priya. I guess the last thing is, if we really want this to be interactive, so if you have questions, feel free to type them in the chat or to use the raise hand feature, and we can unmute you when the system operator is done presenting. We'll be moderating the questions, so ask away. This is meant to benefit you and to help bridge the gap between the AI communities, power system communities, and research. So please feel free to do so. This is also, as Priya mentioned, it's a joint event, part of EPRI's broader AI initiatives. So I'm leading one that's one of the 5 grand challenges in environmental impacts. So EPRI is leading these 5 AI challenges that basically address different areas of electric power that artificial intelligence and machine learning could in which they could potentially make an impact. Environmental impacts in particular focuses on, decarbonization, helping power grids remain sustainable, and in general, helping fight climate change. So we have a monthly meeting that we have that I lead. We have different speakers, we have interactive activities, and we also do, matchmaking activities if you want to work on a proposal or if you want to work on a paper together. So if you're interested in that, please sign up for our mailing list right there, and I can also send it out later. So there's a clickable link.
And this event is also co-hosted by Climate Change AI, which is a global nonprofit initiative to foster impactful work at the intersection of AI, machine learning, and climate action. And if you could go to the next slide, Kyrie. We host a variety of digital resources on this area, events like an upcoming workshop series in a summer school, funding opportunities, an online community discussion platform, webinars like this one, and also a newsletter aggregating events, job opportunities, and other and interesting readings and developments in this particular area. So you can find more information about these on the Climate Change AI website and also by signing up for our newsletter. So with that, we are excited to start the actual program. And so we'll be starting with a presentation from Yicheng Liao from EnergyNet, talking about this first research question about approaches for near real-time modeling and control with large quantities of inverter-based resources. So Yicheng, handing it over to you.
Yeah, I'm here. Yeah. I'm now trying to share my screen. Hello?
Hi, Yicheng. I think we're having a little bit of internet difficulty, but it is starting to share your screen. So we'll let you know when it comes through.
Yeah, it's loading. We can hear you fine though.
Hello?
Yeah, maybe there's an internet.
Yeah, maybe there's an internet
Hello?
difficulty.
Hello? Can you see my?
We can't see your screen, and now your audio is very choppy.
If this
Hello?
is okay, if this is fine with the system operators, maybe does it make sense to go to the next question? So that would be Andrew and Peter from AEMO. If you would be comfortable going now, then we can troubleshoot with Yicheng in the back end.
Yeah, no problem. Yep. Oh.
Okay.
Should I start sharing my screen,
Yeah,
or
go
we?
For it, Peter.
Yeah, okay.
Yeah,
let me
thank
just get this set up. Sorry. Just make sure I've got the presentation up. Sorry, I'm trying to manage 3 screens. Okay, here we go. Can you guys see that?
Yep, we see the slide sorter view. Yeah, and now we see your speaker. Okay, that's right. Good.
Is it all good now? Yeah.
This is great.
All right. No worries. Good morning and good afternoon, everyone. I'm Peter. I'm here from AIMO with Andrew to talk about managing uncertainty in forecasting. So I'm an engineer in the team, and I get involved with the wind and solar registration connection process, and also help set up the initial forecasting models for those wind and solar farms. Andrew is one of the senior data scientists in our team, so he'll be talking about the nitty-gritty AI stuff that we've got later in the presentation. So to begin with, I'll be doing a bit of an introduction about operational forecasting at AIMO. Sorry, it's just something on the screen. Here we go. And then I'll be talking a bit about addressing uncertainty in operational forecasting. So what are some of the changing conditions that we're facing, why it's important to quantify uncertainty, and also the roadmap that we've got planned ahead for our team and AEMO. And then I'll pass over to Andrew to talk, to present a case study about forecasting reserve levels with uncertainty. Okay, so this slide just presents a picture of where our team fits within AEMO. But before I get into that, I'll just on a high level explain what AEMO is. So we're the Australian Energy Market Operator, and we manage the electricity and gas systems and markets across Australia. And our goal is to ensure that Australians have access to affordable, secure and reliable energy. And so with operational forecasting, we work quite closely with two different teams. We work with the controllers in the control room. So that's the box on the left-hand side where it says operations and RTO and GSO. And we also work with staff in the operations planning team, which are involved with outage assessments and operating advices. And so our focus is working on the time frame of 5 minutes. So that's for dispatch, all the way out to 7 days ahead, which is for system adequacy and reserve purposes. We focus on forecasting demand for the NEM, so that's the National Electricity Market, which covers 5 states in Australia. And we also forecast VRE, so that's variable renewable energy, which is comprised of the grid connected wind and solar farms, as well as the rooftop solar PV, less than 100 kilowatts in size. And we also provide situational awareness so that we can communicate uncertainty to the control room and so they can manage that uncertainty. And I'll get into that a bit more detail in the next slide. So what is our vision for operational forecasting? So our vision, we recognize that, that a diverse range of independent forecasts are essential to identifying uncertainty and operational risk. And so we have a challenge that we're currently facing, as with all in ISOs around the world, is that we're increasingly becoming dependent on the weather. So it's the fuel source for wind and solar farms, as well as rooftop PV systems, which affects the variability of supply and demand. And so the deterministic forecast is really becoming less and less meaningful in the energy industry. So there's still a focus for us to improve the forecast accuracy as much as possible. However, it's not really possible to create a perfect forecast as once was thought. So in reality, it's more important for a system operator to have a detailed grasp of risk and uncertainty by providing situational awareness. And situational awareness that we provide to our control room is related to weather events and systems such as severe weather. So this is thunderstorms or high wind speeds leading to turbines cutting out, high temperatures also leading to turbine derating and cutout, as well as inverter derating, rapid cool changes in the system. And all these things contribute to influencing the minimum and maximum demands, load demand in the system. And so that information that we provide is, we provide that to the control room on how they can manage the power system. So for example, how they manage the uncontrolled generation sources from distributed PV systems or some wind farms that are able to operate freely. Also, how they manage the voltage control on the network and so on. And we've also got alerts in place for lightning data, for example, which informs the control room on how to limit flows on impacted transmission lines. And so with all these things said, our vision really is to adopt the best forecasting practices and systems to provide the best situational awareness to a power system operator, which in our case is AEMO. So how do we address uncertainty in operational forecasting? So there are a few changing conditions that we're facing at the moment, some challenges. So with the first item in the top right corner, this really relates to distributed energy resources. So this includes rooftop PV capacity, home batteries, electric vehicles, all these things, the increasing uptake of these things are changing the nature and shape of the demand that must be supplied by the grid. The second thing we have there relates to VRE, so variable renewable energy generation. We're expecting that to increase in Australia significantly over the coming years and over the coming decades, especially now that Australia, many states in Australia have adopted renewable energy targets, and also coal plants are closing earlier than they're initially scheduled. So for example, the largest coal-fired power station in Australia, Eraring, is expected, well, it has just recently announced they're closing 7 years earlier than originally scheduled. So both the demand and VRE forecasts are reliant on weather forecasts. And so this is leading to a greater reliance on quality weather forecasts to produce quality demand and VRE forecasts. And so various teams within AEMO, such as our team and operations planning, as I mentioned earlier, we use this information to be able to make informed decisions, obviously providing that information to the control room and to make informed decisions. And so there are items that, sorry, skip that. There are items that are changing rapidly in the operational environment. So as I mentioned, these things. However, there's also other things that have been changing and new requirements that will change. So in the regulatory work, in the regulatory environment and the market environment, also need to consider changes in these areas. So what that means for us is that we need to develop systems that are flexible and agile to adapt to these changing environments and requirements. And so this just paints a picture of the evolution since market inception. So you can see 1998, the market in the NEM, National Electricity Market, started at that time. And the generation fleet back then was mostly coal and gas, which were able to be dispatched whenever required to meet the demand. So back then it was stable and predictable. We had a stable and predictable demand profile. Hence the scope of control that we had back then was large compared to the uncertainty. And so as the system evolved through the 21st century, we've had coal and gas units retire, and we've had an increased proportion of VRE in the system, which is changing both the supply and demand curves. And so that has ultimately led to less control of supply and more uncertainty in the demand as the energy system is becoming increasingly reliant on and driven by the weather. And so there's every indication that this will continue into the future unless that uncertainty and risk posed by the weather on the supply side, the generation fleet, and the demand side is better managed. So we ultimately need to manage that uncertainty and risk better to ensure that we have a stable grid in the future. And finally, this is our roadmap that we've got planned, and some of these items are have already been implemented and we're working on, and we're looking to improve further. So the top left-hand corner, we've got ensemble forecasting. And so what that is really combining forecasts from a collection of models where ensembles can consist of either multiple forecasts from a single model or ideally a diverse range of forecasts from different models. And so it's really critical to have a strong forecasting practice that can gather and collate forecasts from various models than to simply operate on one model. Bottom left corner, we've got consensus forecasting. So this is an approach for how we use independent forecasts. So a market requires a central forecast to be published to the market. And so this process really analyzes all the forecasts that we have in order to decide the one forecast that is most appropriate, or if there's uncertainty present, adjust the central forecast to account for that uncertainty. Top right corner, probabilistic forecasting is a technique where combining a diversity of forecasting inputs and then assigning a probability to different forecasting outcomes. And so ensemble forecasting is built by simulating a different number of models with varying conditions to derive that probability. And then finally, the forecasting as a service, so we call this FAS. It's a platform that we've established where we can ingest those multiple forecasts from different sources, from different vendors, to support that ensemble forecasting method that I mentioned earlier. And so what I'm trying to say here is that a diversity of forecasting inputs improves the overall situation awareness by indicating the range of potential outcomes for a given condition. And so by combining a number of different forecasts in an objective way, a number of variables can be accounted for, which in turn produces a more effective forecast than any one model that we could have. And so overall, uncertainty, as I mentioned before, uncertainty will only increase as the system evolves and market rules and requirements change. So, we are changing our systems at the moment so we can highlight this operational uncertainty in our forecasts, and so that decision makers within the business can make the best informed decisions by capturing that uncertainty and making sure the grid can be operated in a safe and sustainable way. So that was very quick and on a high level, but I'll pass on to Andrew now, who will talk you through a case study about forecasting reserves with uncertainty. So this is the really deep data science information and AI. So Andrew, over to you.
Yeah, thanks, Pete. Hi, everyone. My name's Andrew. I'm a senior data scientist for the ops forecasting team at AEMO. I know we're kind of close to the 10-minute mark already, so I'll try to get through these slides reasonably quickly and save time for questions. I'm just going to have a quick talk about a quick case study in which we had an initiative that we actually forecast and deliver reserve level forecasting to the control room as well as to other systems that actually has uncertainty in mind. I think it's a really interesting case study to share because it's one of the first initiatives that we did within AEMO that actually addresses uncertainty and actually says, hey, we actually need to change these sort of market initiatives to reflect something that's more probabilistic and dynamic in nature, and actually, addresses the changing nature of the grid. So it's one that's actually a really nice success story for us. The idea behind it is that we need to kind of change the way that we set our reserve levels. So I think quite a few people know it's quite a hard balance to strike those reserve levels. You need a balance on the the increased cost due to spinning reserve on one side versus managing power system security risk on the other. You set your reserve level too high, it means you're incurring additional, possibly unnecessary costs in spinning up that reserve. Set it too low, and it means you could be operating in a state of heightened risk. Next slide. How was this done in the past? Historically, reserve levels were set simply based on the largest supply to the system. So really simply put, you consider the largest or the two largest suppliers to the load in your grid, and you say, hey, if these guys fail for any one reason or another, we need to make sure we have enough reserve available on hand to cover them. So in this case here, we've got coal unit, wind unit, and interconnector from another region supplying load to that little center there. If in this scenario, the coal and the interconnector are the two largest suppliers to the system, they're both equal about 650 megawatts of generation. In this case, we just set our reserve to 650 megawatts. So it's a very static approach. It's one that's really doesn't consider that you can set more optimal levels of reserve if you consider the changing and varying nature of the things that you need reserve for, and that includes addressing the uncertainty that is inherent to it. So, I mean, there's so many different ways in which uncertainty can be addressed here. Each generator or plant has their own unique challenges as to what levels of uncertainty and variability are inherent to it. Even when we're forecasting the load, there can be a different source of error or uncertainty based on the time of day or based on the day of week, and even the forecast horizon or your forecast outlook has different levels of uncertainty associated with it too. If you're 5 minutes ahead, you can be a lot more confident in what you're forecasting compared to if you're 7 days out. So if we go to the next slide, we try to address this by firstly saying, let's get a measurement of uncertainty in our case. So if we say that our reserves is simply our total available supply, minus our demand, then we can say that an uncertainty associated with that reserve level, in which we call the forecast uncertainty measurement, or FUM, is simply just the forecast error of supply minus the forecast error of demand. And it's just a proxy of saying that this can be our historical levels of reserve. And if you actually look at this graph below, that's a 12-hour ahead distribution of what these uncertainty measurements have looked like in the past. Now, what's great is that we got all this information right here about historically what the uncertainty has been saying, what it's been telling us, and we can drill further into this. We can take this distribution and say, cool, let's look at this distribution at 12 hours ahead, at 24 hours ahead, at 2 hours ahead. Let's look at this distribution if we're only focusing on high temperatures or certain times of the day or certain days of the week, or when certain generation supplies were at this fold, or when there was a lot of wind and different weather scenarios. So we have this opportunity to create these really dynamic responses in setting our reserve levels. And that's exactly what we did. You go to the next slide. There we introduced a model that we based on the Bayesian belief network. So if anyone's not familiar with this, I won't go into too much detail, but the BBN, or the Bayesian belief network, it's a probabilistic graphical model, and it represents a set of variables that and their conditional and probabilistic relationships with each other. So left-hand side, you've got those blue nodes that represent all your different inputs into the network. So you can have things like, what your weather forecast is saying, your current temperature, your price forecast, etc. Your green nodes on the right, they represent the actual uncertainty errors at different forecast horizons. So what we're able to do with this sort of model in a very simple, high-level way is we're able to configure the blue nodes to say this is the exact forecasting scenario that we're trying to predict. This is the exact kind of condition as to what we're experiencing and trying to forecast out. And the right-hand side of the node, fantastic. We actually have this historical and probabilistic relationship and distribution of what has happened in the past. So if we then say, cool, let's take the 90th or the 95th or the 98th percentile of each of those distributions, we have this almost like extreme or near maximum way of saying that this is where our reserve should not exceed, or this is where our reserve should not dip below. And that can really help inform us as to whether we're operating in a system of risk, or if we have enough reserve to safely and reliably operate in the future. Go to the next slide. What that visually looks like and how this is actually delivered, simply put, is if we have our forecasted supply, forecasted demand, we calculate our reserve, and then we have what we call our LOR triggers. So that's loss of reserve triggers. And that's the output of the FUM. That's usually based on a probabilistic percentile output of that distribution. And so we simply say, based on these conditions, this is kind of where maybe the 95th percentile of our reserves were. So we want to make sure that our reserve stays above it. If not, we need to raise a trigger. That's going to inform the control room. That's going to inform us. And that can initiate so many different types of market responses. Everything from the supply side to saying, hey, maybe we need to ask more generators to come online and be available, to also the demand side. If there's not enough generation, we could ask some market participants and large load units to maybe shut down for a period, so we make sure that we have enough additional reserve on hand. This is just some mock data, by the way. This is definitely not how it looks, and we definitely do not trigger this many LORs, but I just want to get a visual representation of how it does look. Next slide, I'll just quickly go through this final slide here. Obviously, we also recognize that this is an ongoing process, and we are constantly improving and developing and refining what we do and how we deliver this. So even with the FUM and these uncertainty measurements, we constantly retrain and refine the inputs of the data to make sure that it's always up to date and always has the most recent, most representative information to it. We do a lot of qualitative assessment to it. So we actually go into the outputs of the model and make sure that it's saying what it's supposed to be saying. So we don't really take it as a purely black box solution. We really like to go into it because the output is really important in what it informs decision making. And we're actually working on an initiative right now to disaggregate these uncertainty measures. So we can actually break down the sources of uncertainty even further for more intuitive and improved decision making. So, rather than just having one uncertainty measurement, we can say, well, here's the uncertainty measurement, but here are all the driving attributes to it, whether that's weather, whether that's from VRE, like renewable sources of energy, more traditional sources of energy, or any other factors. So that's kind of the roadmap ahead. That's kind of where we've been, where we're at now, and this is kind of where we'd like to be going with this level of uncertainty. With that, I want to maybe take a pause, and hopefully there's still some time for questions.
All right, thanks, Andrew and Peter, for the helpful insights there. So in order to keep on schedule, I think we actually will move on to the next presentation. But Yi-Cheng, if you want to start sharing your slides while we're setting that up, I think we might have time for one audience question.
Yeah, we can start with the, while Yi-Cheng is setting up, with the first audience question, and I'll store the other ones for maybe Q&A at the very end of this session. So the first question was about kind of the model fidelity in setting up the reserve levels. Is there any measure of congestion in setting reserve levels? Is it a nodal model, meaning you're representing the network, or a lump of all generation and load?
It's a bit of both. Is there a measure of congestion in the reserve levels? So we do. I'm not too sure what I can say that doesn't go into the model, to be honest, but we do definitely consider there are considerations of congestions. There are considerations of what the network conditions and state is like. But there is a lot of post-processes that go on to ensure that what the output of our fund model that we actually deliver is reasonable, and that actually does help solve the way that the grid can actually operate safely, if that makes sense. So even if it's certain aspects of that question isn't directly addressed with our model, there will be post-processes to ensure that it is an accurate and reliable and representative outcome for what the grid can handle in that state. I hope that makes sense.
Yeah, makes sense. Thank you. And yeah, I'll keep these other questions for the end, but Yi-Cheng, why don't you go ahead?
Yeah, me clearly?
Yes. Oops, I think Yi-Cheng, now we cannot hear you. Oh, and now you're muted. Okay, Yi-Cheng, how about I go ahead and try to share your slides and see if that helps your internet stay up a little bit better.
Can you hear me now? Hello, can you hear me?
Yes, we can hear you now.
Yeah, I think this way works better, because whenever I start sharing and try to talk at the same time, it seems like I got lost of the connection. Sorry for the internet issues, but I will now present on this topic. I am a power system engineer from Enignet. I have been working on the power system dynamic statics, mainly focused on the converter-based power system. So today I'm glad that I can share some of our perspectives on how AI can be applied for power system dynamic studies. First of all, I would also like to show my thanks to Jeff below from ERCOT for sharing some good comments on this presentation. Because there is also some audience not from the power domain, so I would like to first introduce the power system development and the dynamic studies and the existing challenges. Then I will briefly introduce some potential AI applications and show with an example. So could you please go to the next slide? Yeah, thank you. Yeah. For our legacy power system, they are mainly dominated by the synchronous generators. The synchronous generators are rotating machines. They can transfer the mechanical power to the electricity, no matter from the hydropower or some fossil fuels. But in recent years, with the more and more integration of renewable energy generation. Please go to the next action. We have some more renewable energy resources integrated into the systems, and some new technologies based on the power electronic converters have been utilized to realize this energy generation and also some transmission. For the modern power systems, whenever we have this distributed renewable generations, that also implies, please go to the next action. There is more room for the data exchange and also management because we have such kind of distributed generation. On the other hand, with the hybrid AC and DC transmission, this also means that there could be more increased complexity in the system modeling and analysis. Next slide. So to understand the challenge for the power system studies, we also need to know what are the features of the modern power system. The intermediate behavior of renewable energy generation resources also bring some new production patterns. This figure shows an estimated production within a year in the Danish system, considering the wind, solar, and also some conventional synchronous generations. We can see over the year, actually, the production from the renewable energies have very large variations, and they can be quite different in different months. So that also introduce a wider range of operating conditions. Whenever we want to ensure the energy balance between the production and the consumption, we need to also investigate more operating conditions among different generation sources. Next slide, please. Compared with the legacy power system, because of the distributed generation, the amount of power electricity
We can't hear you anymore, or maybe it's just me.
No, yeah, Yicheng, I think we lost you again. Oh, I think you're muted actually, Yicheng.
Hello? Sorry, maybe.
Okay, you're back
Hello?
now.
Yeah, sorry, I just realized that. So the power electronics have become more and more compared with the conventional generators. Next action. And on the other hand, the power electronics, they are mainly controlled to realize the power generation and transmission. So they are controlled in a very different way compared with the synchronous generator. Synchronous generators can react very slowly, but the power converters can act much faster. On the other hand, this control of power electronics may also bring some interaction issues. Next slide, please. They can bring some new instability issues. These figures show some instability incidents in recent years caused by converter control interactions. We can find that the oscillation frequency may range from a low frequency to a high frequency, even till a few kilohertz. Next, please. As the power system operator, to ensure the stable operation of the power system, we need to consider two types of analysis. Firstly, that if we do not consider any dynamics, we can focus on the steady state analysis. Next action. Because we need to ensure the balance between the energy production and consumption, so we can solve the nonlinear algebraic equation of the electrical system to solve the power flow to achieve the steady state analysis. But for converter-based system, because the amount of a converter increased, that means that we need higher order system models to conduct these studies. Also, which also requires more effort on the system model aggregation and reduction. Next action, please. But the power system is also operating under the dynamic environment. So we need also to consider large and small signal disturbances by solving the nonlinear differential equations. Whenever we have the power electronic converter, which brings much faster dynamics, we can done the system studies based on simulations with a smaller time step. But on the other hand, it also increases the simulation time. Next slide. If we summarize the challenge of the modern power system, please next action. Because the modern power system dynamic studies, they are mainly based on the mathematical model representation of the equipment and their settings. Next action. The conventional generator-based system, their model can be more easily built because they are based on the physics of the machine and their parameters are relatively consistent during operation. Next. But for power electronic converters, their dynamic behavior relies significantly on their control system and their control parameter settings. The converter algorithm may also be confidential because they are produced by different manufacturers. Sometimes their controller settings can also be changed in the field without notification to engineers performing the dynamic studies. So this also means that we also need to consider the dynamic studies more towards for black box systems. Next slide. On the other hand, the power electronics can be controlled much faster. So please next. So we need more simulation time to realize the simulation with smaller time steps. Next. And the renewable energy generations may also bring a wider range of operating conditions, which also brings more simulation burden. Next. Last but not least, because even though we can conduct the dynamic study based on the simulation, the results are usually based on the time domain waveforms, which can reveal little insight to the system level operation and regulation. Whenever we found some instability issues, we can hardly know what is the reason cause such kind of problems, so which can hardly help us to improve the operation and the regulation at the system level. Next slide. So considering these challenges, we think that AI could be helpful in the following ways. Next, because the AI is the data-driven based approach which works well for black box systems, so it could be helpful for the model identification. In particular, next, the converter-based systems usually have quite different behavior, especially whenever we have a simulation model developed by different converter manufacturers. But the real-life converter systems may also have some deviation from their developed simulation models. So AI may also help us to identify how much difference between our simulation models and the real-life models. Next. And the AI models can compute much faster. So that also means that if we could use AI to train some model for analysis, it can may be helpful to improve the analysis efficiency. And furthermore, we can also consider use those models for online assessment. Next. And also AI is possible to extract some hidden features if we can know, for instance, know what kind of information can help the system level operation and regulation. Maybe some AI-based algorithm can also help us to get those information to help us for system level studies. Next slide. I will next show a very brief example on how AI can be used for the small signal model identification. This was a research when I was a postdoc with KTH Royal Institute of Technology. Here, the idea is that because for power system small signal dynamic studies, we can use the frequency domain analysis. Sometimes we can measure the impedance model of the converter in the simulation and conduct a stability analysis based on the measurement data. But the impedance model is only a small signal model around the one operating conditions. Next, if we need to analyze the power system stability under a wide range of operating conditions, we have to repeat this analysis many times next, which is very time consuming. So I considered how the AI can be used to accelerate the stability analysis. Next slide, please. Because we can, based on the power operating conditions, we can measure the impedance model to conduct the power system studies next. This project was funded by Caesar.ai Digital Transformation Institute, collaborated by KTH and the University of Princeton. We considered how to use the neural network to train the converter impedance models. So in this way, based on the data, we can easily obtain a model which covers all the operating points continuously. That means that whenever we have the power flow analysis, we can more efficiently compute the impedance model to conduct the system level stability analysis, which can speed up our small signal stability studies. Next. Okay, this is the end of my presentation. Thanks for your attention, and I'm looking forward to hear any comments, questions, and also looking forward to the discussions.
All right, thanks so much, Yicheng, for that wonderful and insightful presentation. So to those in the audience, feel free to either drop questions in the chat or raise your hand if you'd like to ask a question. But to start us off, I wanted to communicate one of the questions that was actually submitted ahead when folks registered, which was, and you went into this in your presentation a little bit, but what are the advantages of AI and machine learning for real-time control instead of other conventional controllers? And do you think that hybrid, black box plus physics models could be a reasonable solution to address speed and fidelity?
So you are asking me, right?
Yes.
Yeah.
Yep.
Okay. I think actually, because as a power system operator, we usually the control is mainly developed by the conveyor-based system. We do not care too much how they control the system. We mainly consider if they can achieve the requirement from our grid side. But I could say if when we look at the dynamic studies, we usually consider how they perform. So the most important thing is that we rely on the model to predict the dynamic behavior. For the real time, like as you mentioned, for the control, there could be some ways, but I'm not quite sure if this is of the interest at the system level dynamic studies, because usually whenever we would like to ensure the power balance, the time scales to get these settings for power flow, they are quite slow, which are not highly related to the fast dynamics of the power converter control.
We have a bunch of, thank you. We have a bunch of other questions. So one of them kind of centers on how willing are system operators to use AI for dynamic studies in your experience?
Currently, I think we are still mainly rely on the existing models provided by different vendors. But actually, in the practice, we already found a lot of difference because, for instance, we have some models developed for studies, but if we compare with the real life measurement, there are a lot of difference. Sometimes our existing models cannot really predict the real incident. So that's why I highlight before, we need to get some results from the real measurement. But whenever we have the measurement, we do not know the details, what is behind the data and what is the real world. So in that way, if we can use this to help us to identify the model, then we can better know what are the difference between our existing simulation model and the real world.
Awesome, thank you. So there are a bunch of questions coming in about data. So, how much data is needed to train some of the AI models that you discussed? Where does the data come from? And how can you make sure that if the system shifts, has a distribution shift underneath, and sort of the data maybe doesn't necessarily represent now in the future the situation the model's being used in, how do you deal with that? So a bunch of questions about provenance of data, sort of representativeness of data, and all of that, if you have any comments on that side.
Yeah, I would have to say that how much of data is really important if we want to really use this data for some analysis. But this is also a very open question, because of course in real life we have some measurement, we can always get some data, but as I also highlighted just now, because the converter-based system, they really act much faster. So that also means that sometimes we need the data which are sampled much with a higher resolution. But currently, I think this can also be explored in the future together, based on some collaboration between industry and academia. Because currently, as far as I know, some measurements, they do not have very fast sampling rate. So maybe the data is not sufficient to capture all the dynamics, but this also needs some further studies to check how fast is needed to sampling those data in order to get accurate enough prediction of the model.
And then I think that makes sense. Maybe that brings up some questions about, synthetic data generation as well. But we have time for one more question from the audience. There's one drawback of the AI methods, that these are applied to the network on which they are trained. Are there any methods to generalize the training method where a trained algorithm on one network can be used on another network? So I guess in your experience, what has been the generalizability?
Yeah, I think this is really hard to say, because whenever I think AI is a very efficient tool for us if we want to conduct some studies to achieve some purpose, but we need to also be aware how we should to define this problem to find the suitable AI models to train this. And of course, the real life is always changing. So that also ensure we also need to be aware if we are always using the updated data, if we want to also to ensure that those trained models can capture the real life change. So I would say if we can really define our problem well, and we can first train some model, but of course if we want to keep the dynamic environment, we also need to update the data and keep this model also updated.
Yeah, so wonderful. And editorializing a bit, I think, yeah, combining some of the things from the previous questions about sampling rate for data and generalizability of methods. From my perspective, I think this is why sort of the correct combination of black box modeling with physics-based modeling is going to be necessary to contend with some of these issues as well.
Yes.
Yeah, absolutely. So yeah, thank you so much, Yicheng.
I also thank you, and I hope I explained our ideas clearly and also addressed these questions properly.
Definitely. Yeah, thank you. And for those who had more questions for Yicheng, we'll hopefully be able to also get to some of those during the general Q&A. But now wanted to move on to our final presentation from Mustafa Nick at National Grid ESO, talking about probabilistic planning methods, and I think supplemented afterwards by some insights from Kaiso as well. So Mustafa, please take it away.
Hello.
Hi, we can see the slides.
Hi.
All good.
Yeah. Okay. So all good. Hi everyone. Mustafa Nick. I'm working in network development in National Grid ESO, and I'm leading on the probabilistic network planning for tools development and also methodology. So for this presentation, so I tried to briefly describe what we are doing for the probabilistic planning and also the opportunities for the AI. A brief outline. So I have one slide to show the National Grid ESO planning methodology. Just mention that in UK we have a structure that the system operator is is separate from the transmission owner. So that's why we call ESO, electricity system operator. And so the other topics is developing study scenarios and modeling technique for the planning, and developing network solutions. Then I will discuss about network modeling and optimization technique and tools. And last one about the flexibility assessment and their quantification for long-term planning. In ESO, National Grid ESO, we have an annual cycle for network planning. So the first step is to generate future energy scenarios. So that team every year create 4 different scenarios to show what does the future of the energy look like. So that is more mostly related to the background generation. So the for example, level of nuclear, wind, and where they will be built in the futures. And then we have the electricity 10 years statement that we publish it every November that is called ETES in ETES. So we assess this future energy scenario and to see what does it mean for the network. Here we have 4 background generation, and for each background generation, we have created assessment technique to do year-round probabilistic to see what will be the impact on the network. And also currently we have also studying the network based on the boundaries. So we have the boundaries that we assess the network capability across each boundary. And then the last one, we do the cost benefit assessment and we publish the result in a publication called NOAA Network Option Assessment to see what options are needed to meet the requirement that we identified in the ETES. So this whole process is starting from the generating future energy scenario to proposing option for network development. We do it every year and we update the recommendation every year. Next topic, so that is almost the first step in doing probabilistic planning, is developing scenario and modeling technique. So this scenario are the scenario that we create based on the background generation. So this is different from the 4th scenario that we get from the future energy scenario. And UK is an interesting case study because we have high share of renewables across UK, different wind farms and also solar. And also we have a lot of interconnector that will come in future that will connect UK grid to multiple grid in Europe, in Norway, Belgium, Netherlands, France, Germany, and Ireland. So these all they will have uncertainty across the year for each hour, and they all have temporal and spatial correlation between all of them. Large wind production can impact the interconnector flow to the Europe. Also, any problem or outage in the Europe might change the interconnected flow coming to the UK. So that's why we need to generate multiple scenarios across the year for all the year that we are studying, so that to assess the network capability. These uncertainty also has an impact on the balancing prices. So the way that we do the cost benefit assessment for the UK is that we calculate the net NPV, net present value, for each option and a combination of the options, and compare the investment cost against the reduction in the constraint cost. That if we don't have that option, how much constraint cost will increase in the balancing mechanism in the UK. And also we need another important uncertainty and factor that we need to consider is also the maintenance outages that we need to consider. For example, maintenance outage of a large interconnector or a large nuclear power plant can have a huge impact on the constraint cost and the power flow pattern across the UK network. So all these parameters, so we need to create scenario for them, and then there are a lot of room to improve the current techniques and consider all these correlation and parameters. That's I believe it's difficult, but we achievable in future. But what we currently do is that we use 10 representative climate year scenario, and we have one, so that we have 10 snapshots per hour, and then also Monte Carlo simulation to model some of the generation outages and also demand pattern. Next is that, so the next item after we assess the network is the developing network solutions. So network solution are not, limited to the new circuit or building a new circuit. That's, because I was in academia, so most of the paper are targeting only new circuits, but we have a range of options. So here we can see last year we studied 33 new circuits, but at the same time, we had 26 options for power flow control devices. So these are like phase shifters that can change the power flow across the circuit, or some new equipment based on power electronic that work like phase shifter. So, and also we have the solution based on reconfiguring a substation or updating a substation that sometimes can have a huge impact and bring a lot of benefits. Upgrading existing circuit, we have the assess 23 option for voltage and stability, and also alternative option and ESO-led commercial solution. These are the solutions that we assess based on the concept that we call intertrips. So intertrips are like tripping a generator based on when a line trips. So that in that case, we are sure that post-fault we have more capability and we won't violate any constraint. Most of these solutions currently we are building them based on expert experiences. So, but there is a clear path for AI or machine learning to identify a proposed solution across the network, so that we can use them. And another option, after we identify these solutions, so we need to find the investment path. So which combination of this option from this pool of option can provide the most benefit to the network. And currently, again, this is expert based and based on the heuristic method that's mostly based on greedy algorithm and try and error. And the last item is developing. We need, so in the UK, based on all this power electronic that we will have in the future, we need also a solution for the voltage and stability that AI can better find solution for this problem. So after this solution, so the next step is to assess this solution and do cost benefit assessment. And again here, so I just want to highlight some of the complexity that we have in National Grid, and we address them, but they are not, addressed a lot in the literature from academia. So first we have the increased complexity. So we can see what will the UK grid will look like in future with all these offshore wind farm and all these offshore grid and DC links. That's we'll definitely need to change some of the methodology and optimization technique for the network planning. The other one is that we are not limited only to n-1 contingency. N-1 is also important because, for example, some of the network component, like let's say underground cable or underground DC links, when they have a fault, they can be out for a couple of months, and during that period there could be another fault. So that's why we need to assess n-1 and n-1, n-1 and also we consider the maintenance outages of the equipment, because so that across the year there will be planned outages for some network equipment, and then during that planned outage we might have another fault that we need to consider them. So we have them within our methodology. Optimization techniques for the network planning. So that's based on all this complexity. So the kind of definitely better solution or better modeling for the optimization technique based on optimal power flow. So currently we use optimal power flow based on the augmented DC for that consider the losses, and also a expert-based heuristic or greedy approach to create the paths and then assess the net present value for all this combination of the options. And AI definitely can help on this one to combine maybe heuristic and some convex or optimization technique to provide better solution. And also what we see also in the grid is that voltage and stability constraints sometimes they can be very important, especially, for example, when a synchronous unit is on outage. So that means a big source of voltage support or stability support will be out, and that will limit the transfer capability across the network. So these are all the important aspect about the complexity of the cost-benefit assessment and technical assessment. And the last item that we see and we think that's important is to do flexibility assessment and quantification. So we non-built solution, I mean by the solutions that we can rely on the current existing assets, but use their flexibility instead of building a new solution. So there is a need to identify these non-built solution, for example, the flexibility that DSO can provide, or the flexibility that generator or third party can provide. Another important aspect is to model quantify flexibility resources and see how reliable they are, and also their availability is important because so they can provide solution, but that could be limited for the short period of time. So, but if the constraint is persistent across the network, that means after a couple of hours, then that solution is not there, and because it's already exhausted. And these flexibility, so we have studied storage, demand side response, commercial intertrips, that's automated generation disconnection under certain trips to increase the transfer capability post-fault, and also third-party solutions. What we see here is that the reliability and availability of this solution is compared to the traditional one, like building and transmission network. It's open to challenge and discussion. So AI and doing large scale assessment can quantify their availability and reliability across the network, and then can help to better plan the network against future scenarios. And yeah, that's my last slide.
Thank you so much. We got a lot of good questions. I'll start at the first one that was asked by the audience, which is back in the beginning of your presentation. How do you filter the most practical scenarios rather than exhausting over all the possibilities? So I guess, how did you narrow down those scenarios that you included?
So when we create all the scenarios, so we run them through load flow. So the first step is a DC load, is the augmented DC load flow based on the losses, and that we can solve efficiently across tens of thousands of scenario, and that's the first filter that we have.
Just out of curiosity, augmented DC load flow is DC with some
with losses, and also and so we distributed the slack.
Okay, interesting.
Cool. All right. So one of the audience members asked, they said a lot of these AI solutions seem to provide better solutions for the power grid, which is great, and asked if it's possible to make the link to climate change more explicit. So how much would some of these, desired aspects help reduce emissions or otherwise help combat climate change?
Yeah, so currently, so we can quantify the CO2 emission, the reduction in the CO2 emission and the losses based on each options, and then add them to and then monetize them and add them to the cost benefit assessment. So that's not explicit in the current NOAA approach, but that's a part of the ENTSO-E 10 years development plan. That's so the option that are there. So when we run all the scenario across the year, so we calculate the losses, and based on the losses, we monetize the losses and also increase the amount of CO2, and they will be added to the NPV, net present value of each option. And so the AI part also, so based on my experience, can help a lot on to identify solutions. Because in the UK, so for example, one example is the commercial intertrips. So commercial intertrips, so we have a lot of generators that when we have a fault, then they can identify which one can provide the highest impact or the best solution to decrease the flow over certain lines post-fault. That's currently we do it manually based on expert knowledge.
That makes sense. And then the last question until we move to the general Q&A session, and we'll probably have more questions for you there, Mustafa, but do you think National Grid would be likely to develop these tools in-house, or would that be done with partnerships with academia or research labs?
So yeah, we have developed some of this tool in-house, and also we are currently 2 projects, one with academia, University of Strathclyde, that has been concluded, and also another one with consultancy to develop further so that we can have more view over the probabilistic assessment for voltage and stability. But yeah, we are open for collaboration with academia, definitely.
Wonderful. Thanks, Mustafa. So I think we'll now move on to general Q&A. So for the audience, this is Q&A to both all of the presenters who presented across these 3 questions, and also to some of the other system operators who maybe didn't explicitly present but are here today as well. Feel free to jump in. Also, Mustafa, could you hit stop share? I am seeing my own face right now, I think.
Sorry.
Thank you. Great. So so to any of the system operators who would like to come online to answer any of these questions, please feel free. And audience members, feel free to drop questions in the chat. So one of the first questions that we got actually submitted during registration is to ask some questions about, so today we've talked about ways in which AI and machine learning maybe in part is being used or can be used in the future. But in general, what kinds of algorithms and tools are being used today? For example, are physics-informed AI techniques being used, or interpretable AI techniques being used? What is actually being used in practice? And also asked if there are any stories about successes or failures that folks might be willing to share about actually adopting or implementing these algorithms in practice.
Is it for the ESOs?
Yeah, that's for any of the ISOs. Yeah, so go for it, Mustafa, if you have some thoughts.
I have one example for the solar forecasting in National Grid. So we have been using develop AI technique for solar forecasting, because because we didn't have a good visibility over the solar production, because they are mostly on the consumer side and connected to the DNOs. But recently we have developed a good forecasting technique based on AI that has increased the accuracy by 30% compared to the previous method that we were using.
That's awesome.
Sorry, do you mind repeating that question?
Yeah, so the question was about, and Phil, if you were saying something, you were muted, so just as an FYI. But the question was about, what AI algorithms and tools are actually being used in practice. And then also if there are any stories about successes or failures in adopting or implementing these kinds of algorithms that maybe we can learn from going forward.
Yeah, so I can definitely give a quick response on what we've done in ops forecasting in AMO, because we've adopted a lot of AI machine learning software and techniques. So I did talk about a Bayesian belief network. That was one example of what we've adopted. We use I mean, we are very technology and software agnostic. So we do try a lot of things. In terms of algorithms, we have a lot of success with boosted algorithms in the machine learning space. So XGBoost models, like GBM, even a bit of CapBoost has been utilized. We obviously still use a lot of linear models because we get that additional transparency and insight as to what's happening in the models, because we don't always want to rely on things in a black box, even if there is that trade-off for less accuracy. We typically also use R a lot in-house, a little bit of Python, but I would say about over 90% R. So we develop a lot of dashboards as well to deliver these things, because that's usually done in Shiny, because obviously it's one thing to create these models and output it, but it's no point if we can't actually deliver it in an informative way. I would say that's the main success stories that we've done to date with that. So we develop a whole bunch of algorithms and software. That's the key ones that we utilize.
Thank you.
Sorry, was Phil going to jump in right then?
Yeah, so I just wanted to share a couple of things. It's not necessarily right on point, but maybe some cross-cutting themes here, right? Is that one of the things that we've done is actually try to move to more of a probabilistic approach when we're looking at this. The discussion is really focusing more on resource planning as we think about it today. And so we've actually done a lot of work over these last few years trying to determine, how many runs do we need to make? I mean, what level of accuracy do you really need to get to? And so we spent a lot of time starting off with, as much as 1,000 or more runs, and starting to recognize that the ability to run different situations and different conditions or different sets of scenarios is really helpful. And it's better to do that and make fewer probabilistic runs than it is to let the machines run forever and ever, should we say, right? So reducing the amount of runs from 3,000 cycles to 500 cycles in order to get to something that gives us a little better opportunity to test different conditions, if you will. The other thing I wanted to share is there's a theme here about what's the climate impact. And I just wanted to make the point here that, obviously in general, what we're trying to do is operate these renewables more as we possibly can, and just fill in and operate around them with the GHG emitting resources. So I think optimizing these operational models and inherently, and we expect will inherently reduce GHG emissions. So that's almost a given for us as a system operator. I think our real challenge is if we want to actually talk about what are the impacts of climate change, then the real issue for us is we need all of you, the rest of this community, to tell us, what is climate change going to do? How is it going to affect the solar intensity? How's it going to affect the wind and direction and intensity? What's going to happen with our hydro systems? Those kinds of things. So if we really want to start trying to do some probabilistic planning that's beyond a 10 or 20-year horizon, i.e. more in the climate range horizon, then really what is the data set that we're going to use to support that kind of analysis? So if we want to do probabilistic, we're going to need to have some techniques to add the data to this thing. So I guess that's some opening thoughts. I see Jeff kind of chiming in here. Maybe Jeff wants to add a little bit more context to what I'm saying, but wanted to give you some idea about where we're at and a couple of the challenges that we're having today. So Jeff?
No, we still can't hear you.
Yeah, you might be muted.
Looks like Jeff might be trying to text
Yeah.
me. We can't hear you, Jeff.
Might have to change your audio source, microphone source.
So
Well,
anyway,
Jeff-
I think you see where I was going is I was trying to focus more on the longer term horizon rather than maybe some of the shorter term horizon. And for us, shorter term meaning a year, 2 years, 5 years, and we really start to look further out, then we've got some real challenges in terms of what are the input assumptions.
Yeah, I want to open that question up to all the other grid operators. What are you doing right now to sort of impact, we had a question in the chat about how where is it? How demand is sort of being impacted by climate change and how those are incorporated into forecasting models, or how extreme weather events are incorporated into operational and planning models. If anybody has stories about how your system operator is currently doing that.
Yeah, hi everyone. I can fill that for a bit. So how are we tackling kind of more extreme events? Is that the question? So look, we have various ways. It's definitely a challenge that is constantly evolving. So we don't have the right solution now, and even if we did, that's not necessarily going to be the right solution for tomorrow. But what we do is we need to ensure that we have kind of a suite of information that can actually be used for decision making. So actually, we work a lot with the weather provider, lots of different weather providers to get a whole different kind of more than just a synoptic view of what's going on. We like to look at different probabilistic inputs, say like temperature ranges, weather ranges, different forecasts, stuff like that. We also try to incorporate that into our models, so we can have different probabilistic inputs in our models, so we can actually see different scenarios and simulations and how that actually may affect the overall outcome of both the supply and the demand side of things. We already have different POEs, so like different probabilistic ranges in a lot of our forecasts. So the control room, for example, don't like it when you have so much information to give them. So it's a lot of it. Our job is to create that, is to get that situational awareness and hand that over to the control room, for example. But we also put on their monitoring software things like very standardized, confidence boundaries or probabilistic boundaries, just to kind of represent that there is different that there are different scenarios that can be at play from a forecasting realm, and then try to actually delve more into that. It's talk about what those sources are and how that might play out, and give more handover over time.
In National Grid also, so just on the topic for the how we consider the climate change. So yeah, I'm not directly involved in the team, but we have the EMRT, electricity market reform. So that's as Andrew said, it's not established process yet, but we are doing multiple assessment based on ad hoc studies to see the impact of high impact, low probability events. So we know what would be the impact in the future. So it's not established, but a lot of study are ongoing, and then we are assessing multiple options how to do it, how to quantify them.
Wonderful, thanks. And to Phil's call to action to the community that sort of kicked off this line of discussion, we have an audience member in the chat who has presented, for example, one study on how loads may change with the effect of climate change. So definitely continued call to action to those in the research community looking at this to share their work. Maybe a last question that came in also ahead of time. This question was about interoperability. So of course, many of the questions that you all have presented on tackle different aspects of this issue. AI and other techniques might come in to tackle different aspects of this issue. So how do you make sure that they work well together in an interoperable way? How do you evaluate success of these individual techniques in sort of a broader interoperable system? So that, yeah, the question is how do we actually think about interoperability in general here?
Just one comment, and that's probably, don't remove the human process involved. I would say that we personally are getting very overwhelmed by the amount of information and forecasts and models that we have there, but you still need that layer of human process and just understanding what's actually going on, and just to get through all that noise. That's probably my biggest comment on that one.
Yeah, and just to add to Andrew's point with that human interaction, so we work closely with a meteorologist from the Bureau of Meteorology. They work with us on they're in our offices, so a couple of days a week, and we can call them when we need to as well if they're not in the office. So we work quite closely with them because we're not meteorologists ourselves in our operational forecasting team. So having that expert advice and knowledge about the weather system and changes in the weather and cool changes and extreme heat events, having that knowledge from the meteorologist and getting that information and about the timing and about the possibilities of extremes, having that information and communicating that to the control room is really invaluable. So yeah, with that point that Andrew said, it's quite important rather than just looking at the data and seeing what the maximum forecasts are of the range. Also need that human touch to it just to be able to interpret the data as best as possible so that the control room can be informed on possible scenarios and situations.
Thank you so much. We're at time, but I wanted to leave all the grid operators with one more question. So if you have any closing remarks to the community or sort of calls to action, like Phil put it, that we as researchers should be working on or in industry, what would those be? So AEMO, since you went first, you can close out first.
Collaboration. Collaboration is key. We're all in this together. We don't know, no one has the answers by themselves. That's my only call to action, I guess.
Thank you. Yi Chang.
Yeah, I think I can try to answer in this way because I also actually previously I also worked in academia and now I go to industry. So my feeling is that if we want to do something really good, develop some approach, it is really important that way. We need more communication to understand what is the real problems and challenges. Then because the solution can always be developed, but if we really found the right problems, then we can develop a solution that can really make change to the world. Yeah.
Thank you. Mustafa?
So I think this today this is a great opportunity.
Yes, and thank you for coming too. It's been great.
Yeah, I think also that collaboration and communication, definitely we need to do that. Yeah, I was also in academia, and for example, on the network planning, the assumptions that we see in the paper in the academia are a bit different from the assumption or the limitation that we see, when we plan the network with all these uncertainties and all these background changes. But when we do this collaboration and communication, so that will be helpful because then we can learn from each other. So you are doing the research and then we can apply those research to our work. And all this, work, for example, this optimization or AI, they first started from the academia.
Yeah, absolutely. And then any other system operators want to chime in with any last words?
Yeah, it answers from Guinness. I also like to comment a little one on a new issue, emerging issues about electric vehicles, because that's really a resource we're looking into for the coming decades. I'm saying in Guinness, in Denmark, we expect 1/3 of the vehicles to be electric within this decade. And that's really a very large and powerful resource. So this uncertainties in this resource, we also should be aware and how do we handle this? And it also comes to this system operator, but also DSO cooperation, because that's a resource that could give challenge for the distribution operator, but it's also a resource reflecting on the prices at the SO level. So that's really a new issue to be better knowledge on, and I think that's where AI could be very useful also.
All right. Yeah. Thank you for sharing that. And really thank you to all of the system operators for your amazing insights here. And to all of the audience members for your fantastic questions. As we mentioned at the beginning of the presentation, this is, hopefully just the start of a sort of broader conversation and broader initiative. So we'll follow up with what next steps and ways in which you can sort of continue to interact with maybe those who attended this webinars and the system operators going forward. In addition, thank you to the 3 organizations that co-organized this event. So this is GPST, APRI, and Climate Change AI. And if you're interested in continuing to stay plugged into any of these organizations' events, please consider signing up for the organization's respective newsletters as well. So with that, thanks so much, everyone. Again, thanks again to the system operators, and have a good afternoon, evening, morning, wherever you are.
Thank you. See ya.
Thank you, everybody.
Thank you.
Thank you.